Okay, let's take a look at valves. A valve is something where a fluid goes through. I usually draw it with this sort of symbol, where a fluid goes through m dot with some h in, and then we have some h out times m dot, and p in is greater than p out, so the pressure drops in a valve. And the question is, what's the energy balance revert to? And it is in equals out, or m dot h in equals m dot h out. If we neglect changes in kinetic energy, then we call this a throttling process. Throttling. And that's how we're going to treat most valves. Assume that the change in kinetic energy is small. And so h in equals h out. We can cancel the m dot out. Assume it's at steady state, and what goes in goes out. So h in equals h out for a valve, or we'll call it isenthalpic. Most valves are approximately isenthalpic. And so let's take a look at two types of valve. Let's suppose we have air coming into a valve at 50 psi and coming out at 14.7 psi. Drop it down to atmospheric pressure, 14.7 psi. Coming in we have, suppose it's 250 degrees Fahrenheit. And the question is, what is the temperature out? What is the state coming out of the valve? Now, if we treat the air to be an ideal gas, then you know that delta H is approximately equal to Cp delta T over reasonably small changes in temperature. Well, let's see if it's small. So if delta H is equal to 0 for this valve, and we have an isenthalpic process, then delta T is also equal to 0, must be equal to 0. And so therefore T2 or T out equals T in equals 250 degrees Fahrenheit. So no change in temperature across that valve. Now let's look at another situation similar, but suppose now we put a liquid into the valve instead. We'll take basically the same conditions, except now we have a liquid. We'll take water at 250 degrees Fahrenheit coming into the valve, liquid, and we'll make it liquid by increasing the pressure up to 50 psi above its saturation pressure so that we know it's a liquid, and we'll bring it out at 14.7 psi. Same pressure change for this valve and temperature going in the same, only now we have the liquid coming in. So the question is, what happens in this valve? Well, you know that H2 or H out equals H1. Let's just call this state 1, call this state 2. And so H2 equals H1, and H1 is approximately equal to HF at 250 degrees, which is equal to, oh, let's see, that comes out to about 219 BTUs per pound. So coming out where the pressure is 14.7, we try to determine is a liquid vapor mixture. And we know that H is 219 is greater than HF, which is at the new condition 14.7, HF is 180, and HG, it's less than HG, which is coming out of the valve at 14.7 psi, HG is 1150. So that our 219 falls between there. In fact, so we know it must be a mixture. So in fact, we can calculate the quality here, which I'll do in a minute. But if it's a mixture, and if it's saturated, and the pressure is 14.7, then the temperature must be 212 degrees. So we have nearly a 40-degree drop in temperature across that valve. Now that's a really great thing that we use in refrigeration all the time. We'll put a hot fluid through a valve, hot liquid through a valve, and when it flashes, we call that flashing when it partially vaporizes. some of the energy that's required for vaporization is taken from the fluid itself, so the temperature has to drop. So the temperature dropped all the way from 250 to 212, 40 degrees, almost 40 degrees. Now if we calculate the quality, X out of the valve, X2 is equal to, let's see, 219 minus 180 divided by 1150 minus 180 coming out of the valve, and that comes to approximately 4%. So 4% of it had to vaporize, because it's at this state. To have the constant enthalpy, you're going to need some vapor to accommodate the drop in temperature that you're going to have when you flash down to that new temperature, 212, associated with the pressure. So it came in at 250, went out at 212, a drop of approximately 40 degrees. Now notice that that energy the energy to vaporize is approximately 1,000, let's see, a little under 1,000, 970, but approximately 1,000 BTUs per pound mass. That's Hg minus Hf to vaporize it. And if we took that 1,000 BTUs times 4%, we get about 40 BTUs, which is pretty close to the energy drop of Cp delta T is what? Equal to 38 BTUs, because the delta T is 38 and the, let's say, minus 38. The delta T is 38, 250 minus 212, and the Cp for liquid water, you recall, is 1 BTU per pound. So the energy balance here is that you're not putting heat in. There's no surface area in a valve for heat to come in. Not enough surface area, so heat is small. There's no work coming in or out of the valve, and so the energy, so therefore H1 must be equal to H2, and if it comes out of the valve saturated, which it must, because again the Hn equals H out, so it's between Hg and Hf at this new condition of 14.7. It's really a trade-off of vaporization energy here, vaporization energy, this 4% that's vaporizing, for sensible energy, or delta T energy, of our liquid, and the vapor for that matter, dropping in temperature across the valve. So two very different situations: an ideal gas where the temperature doesn't change, or a liquid which may flash, partially vaporize, and have a radically larger change in temperature.